Hello, in this example, we find the derivative of a function using a method of logarithmic differentiation. And see, what we have here is we have a function that where we do not see any logarithm anywhere. There's no logarithm here. But what we do see is something raised to a power. Well, let me just go ahead and jump in then. So here's our solution. What we do is we apply ln. So what I mean is apply the ln function. And so I'll do that, and I apply it to both sides. And okay, so I've applied logarithm to both sides, and then I expand this expression. So trying to get the right colors. So expand. All right. And what I mean is that I'm going to use that ln of a to the x equals x ln a. That's a property. So that's a property of logarithms. So on the left-hand side, I keep it the same. And the right-hand side, what I'm going to do is take this power, this exponent, and bring it to the front. So I bring that exponent to the front. Now, let me get back to, what's the deal? Why would I even care about this logarithmic differentiation? Well, the deal is that this is a function where we have the base, a function of x, and then we have the power here, a function of x. So we cannot use we can't use a power rule, and we can't use an exponent derivative to do this. So use log differentiation for derivatives of functions in the form y equals f of x, all of it raised to the g of x power. I mean, the directions tell you anyway to use logarithmic differentiation. But so just look at the directions. But anyway, that's when we use that, because there's the only way I know how to take this derivative, but there might be other ways without using logarithm. But okay, so let's get back to this. So with logarithmic differentiation, we apply ln to both sides. And then what we do is we expand. We use properties of logarithms to expand. Here our expansion brings tangent to the front. And the next step, what we're going to do is differentiate. Now, what happens here is that we have on the right-hand side, we have tangent x times ln of the base. That's a product. Okay, so keep that in mind, because when we differentiate, we're going to do the product rule. Also on the left-hand side, we should see that we're going to take the derivative with respect to x, and this is a function of y, ln of y. So when we do differentiate, we are going to use, on the left-hand side, a logarithmic or implicit differentiation. So that's the next thing we're going to do, is differentiate. All right, so the derivative of ln y is 1 over y, y prime. How did that come about? Because if you call this u, or anyways, y, there's no reason to call u, really, but the derivative is 1 over what's inside. It's 1 over u, in this case, 1 over y, but then we multiply by the derivative of what's inside, and that's y prime. That's implicit differentiation. Now over here, we're going to use the product rule. On the right-hand side is over here. The product rule, where we take the derivative of the first function, and then we leave the other function untouched, no derivative. Then the first function is untouched, so it's sum tan x. then ln x 2x to the fourth plus 1 derivative. And of course, you can go ahead and do that step and not do what I'm doing. I'm just sort of writing down the format of the product rule before I actually did the derivative of those terms. So 1 over y prime. Okay, the derivative of tangent x is, you got to use memory, that's secant squared x. And then we have tan x. And now we take the derivative of a log function where this is a log of, we have ln of 2x to the fourth plus 1. So this is a composition. So under this composition, the inside function is u. So the derivative of ln is 1 over u. So that's 1 over 2x to the fourth plus 1. And then we multiply by the derivative of that inside u. Well, what's the derivative of 2x to the fourth plus 1? We use the power rule. By the way, the derivative of constant 1 is 0. So for 2x to the fourth, we use the power rule and we get 2 times 4x to the third. And okay, so this is a multiplication there. That's that big dot multiplication. Then there's a little simplifying, but as we also simplify, another thing we need to do is we need to multiply by y. And the reason for that is that, as we see, this is 1 over y prime equals all this stuff. So we want to just get y prime all by itself. So we're trying to find y prime. That was our goal from the beginning, is differentiate, find y prime. So we have y prime equals, so I multiply by y, big parentheses, secant squared x, ln 2x to the fourth plus 1, plus parentheses tan x, and I'm going to multiply this fraction times this whole expression. This whole expression is a term I made up, sort of, but it's not a fractional expression. So I multiply the numerator times the 1, and I get 2 times 4 is 8. 8x to the third power. Actually, we could multiply the tangent on the top too. That's probably a good idea, but that's a question of style. Maybe I'll do that on the next line. And the parentheses, that's a question. Maybe I won't do that because I sort of like this, the way it looks here, where I have a rational function times a trig function. But that's totally up to see what the author did in the book. This is by the way, I should point out, which I didn't, that this is from OpenStax. Before I end this, I'll put in a little. This is you can get this problem out of the OpenStax textbook, which is free. All right, now what we're going to do is put in y equals this function. So we're going to replace y back by what it is, 2x to the fourth plus 1 raised to the tan x power. So we have y prime equals parentheses 2x to the fourth plus 1 raised to the tan x power. Sort of looks like a lot of stuff here, but anyway. All this other stuff I'm going to copy and paste. I mean, barely I'm going to fit this, it seems. I can move things over, squish it in a little bit. Oh, maybe I should just make this one fraction just to save room. That's just a style choice and also a space choice, how much space I have, whether you want to take that tan x and multiply that, put it in the numerator of the fraction. Same thing, right? Okay, so let me point out that this is found at, put this in a bright color, write this in red. This is from OpenStax.org, and this is Calculus Volume 1, and I believe the section is section 3.8. Well, it sort of might not be that good if I get it wrong, but I think that's it. And it's an example, but I think so, because look, it says 3.81. Yeah, I think that's section 3.8. So that's a free book. You go to the website and there's a digital version. You can buy a hard copy on Amazon for like $40 or in a paperback for like 30. So, but anyway, digital, look it up. They explain everything very well. And so you can get it there. But that's logarithmic differentiation. And by the way, they also show a bunch of work how to do the problem. So you can look at that too. Okay, thank you. Goodbye.